Okay guys, so today we are going to take some familiar information and just kind of build upon it. So what we're looking at here is a silhouette of the periodic table in the background. And what is in this kind of beige tannish color are your S and P sublevel blocks, or more specifically when it comes to valence electrons, it is the groups that have a definite valence electron count. So they always have the same number of electrons in their outermost shell. So that's going to be group 1, group 2, group 13, group 14, 15, 16, 17, 18. So this is something we actually talked about prior to the winter break, where I said that if you look at the S and P blocks, and now that we know what they are, this is your S sublevel block, this is your P sublevel block, that they have consistent valence electron counts. So group 1 always has 1 valence electron, group 2 has 2 valence electrons, group 13 has 3, group 14 has 4, and we can see that with these Lewis dot diagrams that are underneath, or excuse me, with each symbol and within each group. So 6, 7, and then group 18 has 8. Now, the exception with group 18 is helium. So because helium is actually in period 1, all right, so you can see hydrogen is here and helium is here because it's period 1, and we know that period 1 gets, or excuse me, energy level 1 gets filled up with the 1s, and then you move to period 2. Helium is sufficiently filled with 2 valence electrons, okay? So these are our noble gases, all right? And noble gases are the elements, the only elements within the entire periodic table that are completely chemically stable. So these elements don't have to chemically bond and make compounds with other atoms to become chemically stable. So there is a rule known as the octet rule, okay? All right, so the octet rule basically states that an atom is chemically stable with 8 electrons in its valence shell. There are a few exceptions. Helium would be one of them, and the only one that we'll really talk about for now. But overall, as long as an element has 8 valence electrons, then it is chemically stable. So that means that all of these that we see outside of the noble gases need to chemically bond with other atoms in order to become chemically stable. Now, I do want to take just a second to talk about the grayed out section. So that's going to be this section of the transition metals, as well as some of the much larger elements that are in period 7. So these elements do not have a definite number of valence electrons. Do they have to chemically bond to become stable? Most of them do, yes. However, they don't have a set count. So like for instance, iron right here sometimes has 2 valence electrons, sometimes it has 3, sometimes it has 4. So it just depends on that iron atom. So it's these that we look at in the S block and the P block that are always consistent. And it just so happens that the S and the P sublevels are the ones that we always see that are always ahead of like the D sublevel block. So as long as the S sublevel and the P sublevel are filled, then that atom can be stable. So let's take a look at how this really works and kind of put together some elements to see how compounds are formed. Okay, so I've labeled this in such a way so that we can have some really good discussions about and define some things about how these elements are different based on the number of valence electrons they have. So it's important to note that the noble gases right here in yellow, these are already stable, okay? So helium has the 2 that's needed to fill energy level 1, and then all of these have their S and P sublevel blocks filled, which means they have a total of 8 electrons, which makes them chemically stable. Now, all the other elements that you see here are in need of electrons to become stable. So I want to first talk about these 3 groups right here. So this is going to be, if you look at the big table up here or the entire table up here, it's actually smaller, but it's the full table. You've got group 1, group 2, and then group 13 has 1, 2, 3 valence electrons respectively. Now, here's the deal. When an atom has 3 or less valence electrons, what they do to become stable is they will lose their valence electrons in order to become stable, all right? So I know this kind of sounds strange, but they will, because this will allow them to actually have a full valence shell. Now, the ones that have 5, 6, 7 valence electrons, that is, if they have 5 to 7 valence electrons, that would be groups 15, 16, and 17, they are going to gain valence electrons to become stable. And the reasoning behind this is they are very close to becoming stable. Like, they have the majority of the valence electrons they need, so they are closer to 8 than the other groups. So these 3 groups like to gain valence electrons. These are actually called anions. These elements like to become anions, and we will talk more about that in our next chapter in ionic bonding. But for now, just know that these 3 groups, the nitrogen family, oxygen family, and the halogens, like to gain valence electrons to become chemically stable, to get the 8 that they need. Now, groups 1, 2, and 13 will actually lose their valence electrons to become chemically stable. And that is because it takes more energy for them to try to fill up their shell with a total of 8. So just for instance, I could take aluminum. If aluminum gets rid of and loses its 3 valence electrons, it will have a full valence shell underneath if you consider its Bohr model. Okay, so this would be, say, aluminum, all right? And in its Bohr model, we can see here's those first 2 electrons, and then here are the next 8, all right, so that's a total of 10, and here's that third energy shell with the 3 valence electrons that we are looking at right here, okay? So it's got 1, 2, 3 valence electrons. So it will give away these electrons to another atom to become chemically stable. Now, once it does this, okay, what happens is it no longer, once those go away, it no longer has those 3 valence electrons, but as you can see underneath, it has a full valence. Now it has 8, all right? And so every element in these 3 groups will do this. Now hydrogen's kind of an exception, and we'll talk more about that. We're just not ready to really get into that yet, but just know for the most part, what's going to happen with these 3 groups is they will lose those valence electrons to shed their valence shell and have a new valence shell with a total of 8 electrons, or a full valence, okay? Now, as for, let's say we have a different element. So let's say that we have, I'm going to draw another element real quick with its Bohr model so we can kind of visualize this. So if we had oxygen, for example, oxygen, well, I don't want to do that, so let me retry that. All right, let's use a different element so it doesn't look confusing. So let's say we have sulfur, all right, and sulfur has 1, 2, 3. It's in period 3, so it's got 3 shells. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It has 16 total electrons, and here 2, 4, 5, 6 are the valence electrons. So it will gain valence electrons. So it will actually receive electrons from another atom, okay, in order to become chemically stable. And so then once it chemically bonds with another atom and receives these additional 2 electrons it needs, we're going to add that to the valence shell, and you can see now it has the full shell that it needs to be stable. So this is what happens with these elements of the S&P sublevel blocks of the main group elements, all right? So when we consider the 2 elements, sodium and chlorine. So here is sodium. Sodium is actually in group 1. So on the periodic table, it is right here, okay? So it is in group 1. You've got sodium with 1 valence electron, all right? Now you can even see in its electron configuration, it has 1 valence electron because this is the outermost energy shell, okay? So this is energy level 1. This is all of energy level 2. And here's that valence shell, energy level 3, and there's its 1 electron. Now, then you have chlorine. Chlorine is a halogen. Halogens are group 17, and you can see that the halogens have 7 valence electrons. So when we look at chlorine's electron configuration and we see its outermost energy shell, which is energy level 3, which is represented by the large 3, we can see that total, that's 2 plus 5, there's the 7 electrons. So when we're looking at the electron configurations, we can see the valence electron counts. We saw this in our study guide. We saw this referenced in the test, okay, that we just finished from our last unit. But the point being that sodium chloride is a chemical compound that forms regular table salt that we use on our food, okay? So what happens is the electron from sodium is given away to the chlorine atom. So what ends up happening is we end up getting a compound form from two elements complementing each other, okay? So sodium will actually lose this one valence electron and give it away to chlorine that wants to receive it. All right, so I'm going to draw what their electron configurations will look like once this bond takes place. Okay, so here we have it. Sodium, once it gives away its one valence electron to chlorine, chlorine no longer has 7. Chlorine now has 2 plus 6. It now has a total of 8 valence electrons in energy level 3, which is its valence shell. And then sodium, because it lost this one electron, it no longer has an electron in the 3s sublevel. So the energy level 3 is no longer occupied. So now it has a new valence shell, which is energy level 2, that has 2 plus 6. It has 8 valence electrons as well. So this creates a very stable sodium chloride compound. And this is how we are starting to see chemical bonds form. It is a complementary process of where atoms will actually lose and gain electrons with one another in order to become chemically stable. All right? Now, you might be wondering, what about this group right here, group 14? So group 14 is actually, they have 4 valence electrons. So they don't have too many and they don't have too few. So it's like, okay, well, I have 4. I'm not at 8, but I'm not too far away from 8 to lose. So they actually do not lose or gain. They typically will share in order to become stable. So they will share their valence electrons with other atoms, and they actually create what is known as a covalent bond. So that group 14, which has 4 valence electrons, they are known for sharing. The biggest takeaway you guys need to understand is that the groups right here, groups 1, 2, and 13, so up here at the table, groups 1, 2, and 13 are known for losing their valence electrons, while groups 15, 16, and 17 are known for gaining. And what we're seeing now is that these electron configurations, these are what are known as ground state electron configurations, okay? So we've heard that phrase before, ground state, okay? But these are the ground state electron configurations. I'm just putting EC for electron configuration, all right? But we've heard that phrase before, ground state, meaning that's its normal, typical, everyday state before it starts chemically bonding, before it actually is involved in forming bonds with other atoms. So over here, once they actually lose and gain their valence electrons, they become ions. And so this is what is known as an ionic electron configuration, okay? So this is once they have lost or gained electrons to become chemically stable. Okay, so let's take a look at just a couple more of these. Just an example with these where I'm going to take one of the losing atoms and one of the gaining, or one of the elements that loses and one that gains, and form a compound with them. Okay, so there is another example of an element, a bond forming would be, say, with magnesium and fluorine. Okay, that would make magnesium fluoride. All right, so you might be going, okay, well, fluorine only has 7 and magnesium has 2. How's this going to work? Well, here's how it works.
So what happens is magnesium has 2 valence electrons, as we see right here, and we can also see them right here, all right? It needs to lose these in order to become stable, all right? Now, fluorine has 7, so 7 only can receive, fluorine can only receive 1 more. That's all, and you can see in this Lewis dot diagram, it only needs 1 more valence electron. So what happens is it will bond with magnesium, but what happens is you have to have 2 fluorine atoms. Okay, so you can't just have 1, you have to have 2 of them. And what ends up happening is magnesium will donate an electron to each one, okay? So what ends up happening is we have 1 magnesium atom with its 2 valence electrons that's going to donate to 2 fluorine atoms. So its magnesium as an ion, okay, will look like, and I'll explain the charges up here. That we're not really ready for that yet, but magnesium's new electron configuration as an ion is 1s2, 2s2, 2p6. It is now stable because it has 8 total valence electrons. And each of these fluorines, and again, the charges, don't you worry about that right now, but when it becomes an ion, I'm just kind of giving you an idea of why these valence electrons, how they can really show us how chemical bonding takes place, all right? And so each fluorine was 1s2, 2s2, 2p5, but each one received an electron from magnesium, okay? So 1 each, and so now it's this, 1s2, 2s2, 2p6, and so now they have the 8 valence electrons that they need as well to be stable. So everyone's happy, and this creates the compound magnesium fluoride, okay? So that is MgF2. So now we're seeing where these subscripts and formulas come from, because it took 2 of these fluorines, 2 fluorine atoms for every 1 magnesium atom for everyone to be happy and stable. So without using electron configuration, we can see this done with Lewis structures as well. I was showing electron configurations so that you can see how this relates to the unit we just covered and how we can kind of see this falling into place with our upcoming bonding chapters. So I can take this magnesium I just talked about, and it's got 2 valence electrons in the fluorine that I was just using, okay? And the fluorine needs 1 valence electron. So it takes, it's kind of like you couldn't have a bicycle with just 1 tire and a frame. You have to have 2 tires to 1 frame. So in order for magnesium fluoride to create, you have to have 1 magnesium atom, 1 atom of magnesium, but you have to have 2 atoms of fluorine, because magnesium has to get rid of this other valence electron to be stable, so you have to have 2. All right, and so that's what we see happening here, and so that makes MgF2, magnesium fluoride, because you have, it is a 1-to-2 ratio, 1 magnesium to 2 fluorines. And so we haven't got truly to naming and all this stuff, but really important to know the valence electrons and know how we can use these and manipulate Lewis structures or electron configurations in order to see bonding taking place. You'll have a video mini quiz after this video lesson, so just make sure you took notes and be prepared.